We have a triangle here, and if the perimeter is fixed, then how can we reshape it to get maximum area? I have actually done a video about reshaping a rectangle in order to produce the maximum area, and you can check it out if you want to. However, to prove the answer for this question is going to be harder. I'll tell you right now that you have to reshape it into an equilateral triangle to maximize area. That's obviously not the scale. So how can we prove this? Well, we're actually going to use a formula called Heron's formula. Now, Heron's formula states that the area of any triangle is equal to the square root of s times s minus a times s minus b times s minus c. Now, a, b, c are the side lengths of the triangle, and s is the semi-perimeter of the triangle. That is, it's equal to a plus b plus c over 2. So then, for the area of an equilateral triangle, this must mean that using Heron's formula, a is equal to b and is also equal to c, right? So this must mean that s would be equal to 3a over 2. And it's also equal to 3b over 2, as well as 3c over 2. And also, if we rearrange for a, b, c in terms of s, we get that a is equal to 2 over 3s, b is also equal to 2 over 3s, and c is also equal to 2 over 3s. Then let's substitute a, b, c with 2 over 3s each. So we just get s times s minus 2 over 3s times s minus 2 over 3s times s minus 2 over 3s, like this. And then now let's simplify what we see in the brackets. Then we just get, again, the square root of, we have s times 1 over 3s times 1 over 3s times 1 over 3s. So then simplifying even further, you just get that this is the square root of s to the 4 over 27. Now, what we have to do is we have to compare between AE and A, the general A, that is. So, which one is bigger, this or this? Well, notice that if we want to compare these two values, we just have to compare what's inside the square root, right? Because, for example, if I told you to compare between the square root of 15 and square root of 13, even though you might not know the exact values, you can say that, okay, well, 15 is greater than 13, so then the square root of 15 must be greater than the square root of 13. So then, what we are actually comparing is s to the 4 over 27 and s times s minus a times s minus b times s minus c. Now, s to the 4 over here, you can write this as s times s to the 3, right? Now, notice that both of them have an s multiplied together. So then, since they already have a factor of s, you just have to compare the thing that is multiplied to that factor of s, right? So then all you're comparing are the parts circled in red. So we can just erase this s over here. Okay, so now we're going to have to use a very useful fact. First, let's remember, our claim was that this is greater or equal to this, right? Now, I wrote equal here because if a equals to b equals to c, then it would be equal. But otherwise, it would be greater. So this was our original claim. This is greater or equal to this. But how do we prove that? Well, I'm going to tell you a very useful fact for this one. If we have a list of numbers, n1, n2, n3, all the way to nm, and if they're all positive, then the arithmetic mean over here would be equal to n1 plus n2 plus n3 plus all the way to nm over m. You're probably familiar with this arithmetic mean already. And by the way, I know that this can also be applied with negative numbers, but the fact that I'm going to mention following this will require all of these numbers to be positive. But otherwise, this is the arithmetic mean. And we also have something called the geometric mean. The geometric mean of a list of these numbers would be equal to, alright, gm is equal to the product of all of those numbers, n1 times n2 times n3 times all the way to nm, and then you have to take the mth root of the product. Now, here is the fact. The arithmetic mean of a certain set of numbers is always going to be greater or equal to than its geometric mean. And now this is where all of these numbers have to be positive in order for this to work. If you want me to make a video about proving this, then I can do that. However, for now, I'll just tell you this fact as something we have to use right now. Take a look at this right side. What is the arithmetic mean of all three of these numbers? Or all three of these factors? The arithmetic mean, this right here would just be s minus a plus s minus b plus s minus c all over 3. Now if you were to simplify this, you get 3s, and then here you have minus a minus b minus c. This will just be minus a plus b plus c over 2. But wait a minute, what is a plus b plus c? Notice this. A plus b plus c is just equal to 2s, right? We have 3s minus 2s over 3, and now this numerator we have s over 3. And now, let's take a look at the geometric mean. GM of the exact same three numbers. The geometric mean would just be the cube root of s minus a times s minus b times s minus c. Okay, now I'm going to erase all this over here. So now, let's examine. If the arithmetic mean is going to be greater or equal to the geometric mean all the times, in this case, then it should follow that the arithmetic mean cubed should always be greater or equal to the geometric mean cubed, right? So then, what is the arithmetic mean cubed? It's s cubed over 27, right? And the geometric mean, what's its cube? It's just without the cube root, right? So that's just s minus a times s minus b times s minus c. So notice that what we just did is we just proved that s cubed over 27 is always going to be greater or equal to s minus a times s minus b times s minus c. Okay, so, okay, we proved this, so what? Well, notice that we just proved this. We just proved this. This is the exact thing that we were trying to prove. So, since we proved that this is indeed greater or equal to this, we can write a greater or equal to sign in this case. And that's our proof. That is our proof that an equilateral triangle will always have the maximum area. Please let me know what you think in the comments. And thank you for watching. Bye.